Hello, my name is Elise, and my teammates are Jasmine and Drew, and we are the Peter Parker team.
Okay, so our main problem is that drivers often have like a really hard time finding parking in densely populated urban areas like LA. So one example user scenario could be like maybe they want to go to a basketball like NBA game, like a Lakers game. They can just enter like a place like Crypto Arena, um, assuming and then maybe like adjust their budget and stay duration preferences. And once they click begin journey to find the ranked parking spots, the app will return ranked nearby meters based on the query that was sent. And the output will basically just be like a scrollable list of UI cards showing the top parking options, ranked where the ranking is influenced by user preferences. And each of these cards will show the cost, estimated walking time, not the distance, and the time limit for the spot. So how does our system work in a nutshell? It basically first like data from the layout inventory and occupancy API is pulled from there and then cleaned into a candidate meter structure representation. And then it's basically fed back into our geohash index, which our retrieve via the retrieval service, which our retrieval service uses to obtain nearby candidate meters based on their geohash. Then after that, the ranking comes into play, which basically uses a weighted rule-based preference scoring. And then our UI basically displays the results.
So the way that our data ingestion works is that we have a LA dot API client, and this is essentially a very large database of or data set of all of the meter locations in the Los Angeles region, including all the rates, time limits, and other metadata about the meter. The second data set we have is the occupancy API, and this includes the vacancy or occupied statuses of each of those meters. For pre-processing, we take all of the meter locations, which are represented as addresses, and then we translate those into lat longs. Something else that we have developed is a Supabase provider to store all of these cache or store these meters inside of a cache. This is something that's still a work in progress in terms of integrating it fully with our system, but we have gotten it to successfully upload new data into the database. In terms of the way that we retrieve meters, we use a geocoded area. So we have all the retrieved meters, and then we have a or we code a 1 mile radius around those meters, and then fetch all of those meters within that 1 mile radius. And then based on that, we create a geohash index. So when we retrieve new meters, we can retrieve all of the surrounding meters instead of just those inside of the location.
Okay, so in terms of our personal model, we have three. So for our, we have two main attributes: the budget preference and the stay duration preference. So the budget category includes three categorical preferences: low, medium, high, and these basically like encode like how sensitive the user is to prices. Where a low budget would indicate that they're really sensitive to prices and they want something cheap. High would mean that they don't really care and they're pretty flexible. Duration basically like encodes how long the user would want to stay parked. Short being they're usually parked for a short amount of time, long being they want to park for a long amount of time. And ranking basically uses a personal model to score parking spots relative to one another, prioritizing spots that more closely align with the user's preferences. Okay, in terms of context, we use current location, and that's our implicit context signal. The current location is used as a tiebreaker for when two or more parking spots are equidistant from the final destination, encouraging the final ranking to be slightly more nudged towards spots that are closer to the user.
So for our ranking engine, it will take in candidate parking meters that have already been retrieved from the LODLT, and these are basically filtered to nearby and relevant before we even start the scoring. And for our personalization, our ranking will adapt to user preferences. More specifically, each meter has scores, budget, and time limit, each scale to 0 to 1. The weights are applied to these three scores and shift based on user preferences. So for instance, someone with a lower budget will prioritize cheaper meters, while someone with longer might prioritize time limits. And to keep these efficient, we will use haversine distance as a quick approximation to pre-rank meters and avoid expensive API calls. And then we'll get the top 30 meters from that. Then we'll use a blended signal. 85% will come from the OSRM routing API, which will give us the actual pedestrian walking path from the meter to the user's destination. And the remaining 15% will come from haverside measuring how close the meter is to your user's current location. And like I said before, that will act as a tiebreaker. And this hybrid approach will balance both accuracy and performance. And then the final score will weight all three scores combined into a single score using the formula over here.
This is our app. Just for a little bit of context into what you see here, we have a terminal that basically shows what's going on in the back end. We have a little debug log over here so you can see personal model inputs, or sorry, outputs, and of course our front user-facing user interface. So let's get started. First, we will log in as user one. Type in the password and log in. So you can see that the preferences, as shown by the debug log, are set to low and short. And yeah, the text input destination is already pre-filled to crypto.com arena. So let's go there. Let's just see what Laker games there are. No, because we're using the more accurate OSRM distance, it's going to take a bit longer in order to get like more accurate meters. But you can see in our um, terminal output showcasing the backend output, you can see that many OSRM calls are being made, showing that the app is working in the backend. And after a little bit of waiting, we should eventually get our output. Yeah, right about now. So the app UI instantly zooms into where the parking spots are. And if we zoom in just a little bit out, we can confirm that they're close to the crypto.com arena. And let's scroll through our output. So we can see that meters CB254A is ranked first with a roughly estimated walking time of 14 minutes. And as we scroll down, we can see that because price is a low price preference is preferred by the user, prices that have like an estimated total cost that are much cheaper are prioritized higher than more expensive ones. And according to all of these spots, the time duration is pretty much the same. So that doesn't really, so the ranking with respect to that doesn't change too much. But yeah, we can select a spot and it'll show like a full route. And this, just to clarify, this is Apple's MK directions route. This is simply for cosmetic purposes, pretty visualization, just to make the app look more nicer. Doesn't have anything to do with the actual ranking process. And this route does not relate to OSRM and our OSRM implementation anyway. It is just a cosmetic visualization to make the UI more appealing for the user. And maybe, and if we look over to our terminal input, we can see, and if I can just move the panel slightly, we can see that we're getting live data from the occupancy API in LADOT. And if you look at the bottom left corner, yeah, right here, you will have seen that the timestamp recently changed, showing that we're constantly getting live data from the occupancy data API, which is part of our event-driven architecture. Now, let's say I want to do like a vacant option. We'll just select that, end our journey. And if we end our journey, we will see all the spots that we visited, the journey duration, and the final destination that we chose. Let's try another scenario. I'll log out, and this time I'll try being user 3 instead. User 3 is like the rich kid. He can, oh, yeah, you can create an account if you want, but I'm not going to get into that right now. Okay, so user 3 has different preferences. They prefer higher, they can afford to pay a lot, and I guess they're fine with the long parking duration as a result. And because we're a rich kid, maybe we want to go to Dodger Stadium just to watch a Dodger game. So we'll do the whole process again. Added 200 meters, Supabase, 69 meters written to Supabase, our OSRM calls. Eventually, we will get our ranking results, so we will just sit tight until that happens. Okay, so we see each of our different um, positions, or sorry, parking spots, and it automatically zooms in over there. The prices are a lot more expensive since we're prioritizing a longer time limit. And we can see that spots that have like 240-minute time limit are ranked higher than ones that have it 120 minute time limit, showing that the ranking is prioritizing spots that have like a longer duration. Hey, okay, now I'm going to show how the personal model changes the personal model leads to changes in the ranking. So first we'll go to Dodger Stadium with low and short preferences. Okay, and we get our ranked results. We can see that because we prioritize lower prices, we get parking meters who have like a much cheaper hourly rate and therefore a much cheaper estimated total cost, which factors in the duration. And yeah, now let's say we're like a rich guy and we don't mind paying higher prices for a longer stay duration. And let's just see how the results change. Just let it keep going until we get the results. And here they are. So we can see that the prices have actually changed to be a lot more expensive because the user is now prioritizing, because now the ranking is prioritized towards higher costs. Interestingly, the durations seem to be the same, but this is a result of the characteristics, but this can be attributed to like the results of the characteristics of the parking spots that are just like, simply near the Dodger Stadium. If there were any parking spots that happen to have shorter time limit durations than in the previous preferences setup, we would have gotten parking spots that had a much lower time limit.
So if we had more time, we want to optimize our API calls. As you saw in the demo, it takes around 3 to 9 seconds. And we thought that we could optimize it through either caching or tuning the top candidate meter limit.